Hey everyone, this is Dr. Walker. This is video 586, integral form of Faraday's law. We've seen Faraday's law, and it tells us that the EMF induced in a loop is equal to the negative rate of change of the magnetic flux through that loop. What we're going to do in this video is just rewrite Faraday's law, slightly different form called the integral form. And the way we do that is by realizing that the EMF for any closed path can be expressed as this line integral of E dot ds over that path. So this should look very similar to a definition of voltage that we had earlier. So with this definition, we can now look at Faraday's law like this, part that I put the rectangle over. And what it tells us is that whenever you have a changing magnetic field, that's going to induce an electric field. So a changing magnetic flux is not only going to induce an EMF, which induces a current, but it also induces an electric field. And it turns out that there's going to be an electric field induced whether or not there's a loop there. As long as you have a changing field, there will be an induced electric field. Let's take a look at the following example here to kind of get an idea of the direction of the induced electric field. Once we go over this example, then I encourage you to go back to the previous slide to make sure that you can tell why that induced electric field in the previous slide was counterclockwise. So here we have a magnetic field and we're told that it's decreasing within this area here. What is the induced electric field in this area here? So if you want to, take a shot at it, definitely pause the video. But let's talk through this. So we know that when there's a changing magnetic flux, there's going to be a current induced. Imagine that there was a loop here. Which way would the current be? Well, using Lenz's law, I like my four-step process, right? The B external is out of the page, the flux is decreasing, so the induced field is going to be in the same direction out of the page. And then we use right-hand rule number 3 with our thumb pointing direction of the magnetic field out of the page. That tells us that our fingers are curling in the direction of the induced current, which is counterclockwise. Hopefully you're following along with me with these 4 steps here. So if we have an induced current counterclockwise, the electric field is going to be in the same direction. So the electric field will also be counterclockwise. And it's there whether or not there's a loop, so it's just the electric field just makes circles with this changing magnetic field. It makes sense that the electric field goes in the same direction as the current because current is defined as the flow of positive charges, and we know that our positive charges, they do experience a force in the direction of that electric field. So we will do another example in the guide examples where we can find exactly what is the strength of that electric field that is induced.